Hello everyone, this is team number 8011C for the Texas Instruments Analog Design Contest 2012-2013. So as we can see for phase 1A, our problem statement is as shown in the following diagram. It's a Tau Thomas biquad filter. Thomas biquad filter is divided in three stages. The first stage being a low pass filter, the second stage being as shown here is an integrator circuit, and the third stage being an inverting amplifier. Now the hardware implementation of the circuit can be found on the ASLK hardware kit provided by the Texas Instruments to us. So this is the kit on which we worked on, the ASLK 2010 starter kit. Now as we can see, we use the first op amp here. Since it's a dual op amp IC, we use this dual op amp IC for building the first and the second stage of our filter, and this IC is the third stage, which is the inverting amplifier. Now after the hardware implementation, let's move on to the software implementation of the same circuit. As you can see, this is the same circuit, Tau Thomas biquad filter, the first stage, the second stage and the third stage, which is being implemented in the software simulation on the National Instruments Multisim 11.0 version. So let's simulate this circuit and see what happens. So this is the Bode plotter, this is the oscilloscope, and this is the function generator where we are providing a sine wave of peak to peak 1 voltage. So let's see the output of the Bode plotter. So as you can see, this is the magnitude Bode plot of our filter, and we can clearly see the output response is as desired. Now let's see what is the cutoff frequency for this filter. So we can see at a frequency of 201.327 Hz, we see that the cutoff frequency is achieved, that is minus 3 dB, which is equivalent to 1 by root 2 of gain. So as we can see, the cutoff frequency for this filter turns out to be around 201.327 Hz, which will later be verified from the readings on the hardware simulation.
As we can see here, the input is 1 volt peak to peak of frequency 100 Hz. That is being fed to the ASLK kit, that is our Tau Thomas low pass filter. And here, if we increase the frequency from 100 Hz, we see the output change. So as we see, around 229 Hz, the output starts decreasing, and as we increase the frequency further, it nearly decays.
Now at the end of the experiment, what we came to understand is that Tau Thomas filter is a multi-amplifier active filter that has the advantage of ease of design. Now it has a very flexible circuit structure in which the transfer function properties are easily manipulated by modifying the passive RNC elements that connect to the op amps, which is clearly visible if we take a look at the transfer function of the Tau Thomas biquad filter, that by just changing the passive elements RNC connected to the op amps, we can change the properties of the filter. Now, as the circuit contains various modules like we showed the first, second and the third one, the troubleshooting is much simpler. Due to these stages, the center frequency, Q and the gain can easily be independently adjusted. Now because each of these properties are controlled by each of these different modules, and by varying the properties of these modules by varying the RNC elements, these properties can be easily manipulated, such as the center frequency, the Q and the gain. Now we'll move on to the challenges faced by us in the particular experiment. As the experiment demands, we need to compare the readings of the hardware and the software simulation. Now one of the main challenges that we faced was that during the hardware implementation, the accuracy of the output readings is limited by the oscilloscope, and thus a slight discrepancy was found in the software and the hardware readings. Now the second discrepancy that we found, or the challenge that we found, was that now these two LEDs, the plus 10 and minus 10 LEDs, are supposed to glow when a correct power supply of plus 10 and minus 10 volt is given to the board. He initially gave a supply of just 10 volt, that is a regulated power supply of 0 to 10 volt. Even then these two LEDs were found to glow. Because of that, the first instance when we conducted the experiment, readings did not match with the software simulation. But later, when plus 10 and minus 10 readings were given, the readings were found to be correct. So one of the main problems that we faced was that the LEDs being blown even when the proper power supply was not given to the board. The new inferences learned by, one of the most important inference learned by us in this experiment was that we were extremely fascinated by seeing the use of multiplier to form a voltage controlled filter to change the bandwidth because otherwise the only way we were aware of changing the bandwidth was by changing the properties of the filter. But this new concept opens new ways to exploit the properties of a multiplier, and we will definitely use this new knowledge further in our projects. So thank you.